Hello everybody, and welcome back to another Eng 130 video tutorial. Now in this week 4, we're going to be covering something called moments. And moments I've kind of hinted about before. It's usually what happens when forces on a body don't all act at the same point. What we've done in the past for particle equilibrium is we'd have all those forces act at the exact same point. And because of that, there is no rotation of that point. However, of course, we live in a 3D world. Everything doesn't always act at a single point. And the best example of that is a beam. And the reason why I say a beam is because you guys will see beams a lot moving forward. And as you guys know, for beams, they're basically just these big, long, slender members, and the forces could be anywhere along that beam. And they won't always act at the same point. Now, if you have two forces that don't act at the same point, you'll typically see a rotation. And we'll cover that in this example. So with that being said, let's get started. Alrighty, so in this example, what it says is it wants us to determine the moment about point B. So let's highlight that real quick, point B, because that'll be very, very important, as you guys will see. Of each of the three forces acting on a beam. So of course we have a beam, kind of hinted to, we're going to have a lot of beams. But before we begin into that, let's just discuss what moments are. And basically it's like this. Let's take a nice beam. Come on, there we go. So not the best. Oh, okay. Actually, I think I'm just going to draw a nice rectangle. I forgot that I can do this. All right, so good enough. So if we had two forces on this beam, which I'm going to label in red. So we have an F1 and we have an F2. And the forces were located at those points. So of course their line of action will be intercepting the same point right here. Now this beam, depending on the magnitude of these forces, so let's say that the force at the bottom is 20 kilonewtons and the force at the top here is 50 kilonewtons. What we'd expect is this beam to move just vertically downwards. So its final position may be this green beam right here. Yeah, something like that. So just pretend that this is the same. That's how its final position would go. It doesn't rotate, it just kind of translates straight down. So now let's go to a second scenario. So let's keep that 50 right there. So we'll keep that. But instead, let's take this other point and let's put it down here. And let's keep this 20 kilonewtons. So this will remain the exact same. So 20 kilonewtons. The only difference is we shifted it at a distance, let's just say x. So the only difference is we move this a distance x from the original point. So as you guys can imagine, one of the things the beam's going to do, of course, is there's still more force going vertically downwards than there is upwards. So the beam will actually still move downwards as so. The only difference now is that it's going to start to rotate because of that difference in, well, moment, realistically. So what's going to happen is the beam will actually start to look like this in the end. Oh, this doesn't really help me correct it, so let me just kind of draw a fake beam by myself, like this. So this is kind of what you would see. It still moves downwards, but it also has that rotation. Because what happens is this force right here, if we're taking moments, what it is it's going to be this force. Oh, I shouldn't have done it in red. If I'm taking the moment about this point A, what it's going to be is it's going to be any force that does not act through it. So the 50, it goes through point A, it won't create a moment. However, this 20 kilonewtons does not act through point A, so the moment at A, due to the 20 kilonewtons, is just going to be the force times the distance, and this is the perpendicular distance. And what I mean by that is if I were to draw a line across, and then a line where the force is going, this has to be 90 degrees. Has to be 90 degrees. If I were to draw another line, let's say like this, and the force intercepts here, and I use, and I'll do this in pink so everyone can see, I use this distance, that would be very incorrect. That is not the correct distance. It has to be that perpendicular distance. In this case, that'd be x. So we're just going to go through a quick example here. This example is, it's very, very nice. It's very, very short, but unfortunately for you guys, it's probably not what you're going to see on a midterm. As you guys have probably seen with the theme with particle equilibrium, the midterm usually doesn't like giving you 2D examples. So as you guys may guess, we're going to deal with moments in 3D later on, but we'll get to those. However, the concepts of 2D are very important because in the second half of the course, we deal with equilibrium again, not particle equilibrium, but just regular equilibrium. And in that case, we have to take the sum of the moments. And it's usually 2D cases, so this is very, very important. The only thing students really mess up on is just the sign of the moments. So we'll talk about that in a couple seconds. So the first thing that we have to do, and for any scenario, like I said, we have to start drawing free body diagrams. Free body diagrams are very, 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 very important. So in this case, what we have is we're going to have a beam. So I'm just going to draw a rectangle. So for you guys, I just recommend using your rulers, the ruler to draw a simple beam. And then we're going to start putting all the forces onto the beam. So what I'm going to do in red is I'm going to put all the external forces on. So the external forces. So we see that because of F1, we have a force that comes downwards right here. And I'm just going to label it as 375. And what I'm going to do is I'm going to put newtons. Again, even though these examples are in imperial units, we're going to just swap that to newtons, make our lives a little bit easier. And then, of course, over here, we have another force kind of coming in at an angle, like so. So I'm just going to put that there. And I'm going to put 500 newtons. And then we also have a third force that's acting at the very bottom, and it's coming up to the side and going downwards. And this one is 160 newtons. So now that we put the forces on, we also have to add those extra details I discussed in the previous week, which are the angles of all the forces. So if we look at the 500, we see that it gives us a nice little triangle. So we're just going to replicate that and go, this is 4, 3, and 5. And then, of course, for the 160, it gives us an angle and not a triangle. So we know that this right here is going to be 30 degrees. So, as I also said in particle equilibrium, all the forces act at the same point. So in those free body diagrams, we rarely have to deal with distances, any sort of lengths. However, in beams, when we're dealing with moments, and moments are dependent on those lengths, we have to make sure that we include the distances between the forces in our free body diagram. So at the bottom here, I'm just going to draw a line, and I'm going to go from here to here, then from here to here, and then from here to here. And we're going to switch all the feet to meters. Again, we're going to just try and stay in those SI units. So right here, what we're going to have is 8 meters. Then this is going to be 6 meters. And then this one's going to be 5 meters. So this is all we'll need for this question. But it's best to also include support reactions. So even though you guys may not know this yet, or it doesn't even matter, don't worry about this, because they'll more specifically say what kind of reactions these are. At A there, it would actually be, looks like more of a fixed support because we're restraining those flanges. But again, you guys don't have to worry about that. We'll tell you if it's a fixed support. You'll never have to guess. But it's just good habit that when you're drawing these free body diagrams, you also think about those external reactions. And it's not for right now. It's for in the second half of the course. But again, the reactions won't be like this, where this is kind of confusing what's going on at A. We'll either give you a very distinct roller or a very distinct pin or fixed connection. And also in the question, we'll tell you what kind of connection it is. So you don't have to worry about trying and guessing. But in this case, we have, I'm assuming, fixed connection. So what's going to happen is there's going to be 3 external forces. They're going to be 2 just regular forces, one vertically, one horizontally, but then it's also fixed, so it prevents that rotation. So there's also a third force right here. So how I would label these is I would just go R, Y, RX, and M. So those are just my support reactions. Again, we don't need them for this question. What we do want for this question, though, which is probably very, very good to have, is it wants us to take the moments about point B. So what I'm going to do is I'm just going to label point B, and then that also showed me that I realized I'm actually missing a distance. We also care about this distance, which is 0.5 meters. So this right here would be a good free body diagram for the second half of the course when you're dealing with beams a lot. So it's just good to be ready for. In this example, though, it's a little bit easier. And one thing I should just kind of show you guys right now is if we look here, I have 8 meters and I also have 6 meters. But in my diagram, the 6 meters is longer than the 8 meters. That's fine, as long as it's nice and neat and you can still see what's going on. Again, these don't have to be perfectly to scale. You should try your best, but we're not going to be too crazy on docking marks or anything like that. So that being said, let's start determining the moments. So remember what I said about moments. Moments are the perpendicular distance times the force. So if we look right here, and I'm going to actually take pink, and pink is going to be the color I use to define that perpendicular distance. And what we're going to do is we're going to start with F1. So right here, I'm just going to put F1, and we know that the moment, F1. So I'm going to say that moment 1 is equal to F1, because we know it's the force, times the perpendicular distance. So remember what we want is we want that 90-degree angle between the force and then the kind of the position vector, but you guys will get into that later. It's the distance between the points. So if I were to draw this pink line right here, I actually see that my force, F1, the 375, it's actually already at 90 degrees. It's actually really easy to tell. So from here, we know that M1 is going to be equal to the force F1. So we're going to have 375 and then times that distance. And we know that distance is just going to be the 6 meters plus the 5 meters. So when you put all that together, what you get is the moment is going to be equal to 4,125 Newton times meters. So that's also very important. It's just the units of moment. So what we're doing in the formula is we're taking a force times the distance. So as you would expect, the units, of course, are going to be units of force times units of distance. So Newton meters. However, this question is not quite done yet, because one of the most important things that we have to do with moments, and this is what will get most of you guys on the midterms and stuff like that, is we have to define the direction. So there's two directions we can choose from. And the first one is what we call counterclockwise, and then the second one is clockwise. So you guys want a hint at which way they go? Just look at a clock. Counterclockwise or clockwise. But at the end of this answer here, we need to put one of those values. So there are many ways to do this, but I find the best is just to visualize it. Oops, that's not what I wanted to do. I just wanted to get rid of the pink line, but I don't know if that's going to be possible. All right, so pink line is going to stay for a little bit. All right, so the best way to visualize what I like to do is I like to take my pencil, and this is going to be hard because I can't really show you, but I'm going to draw it out. And what I do with my pencil is at the bottom of the pencil, I pretend it's that point I'm taking the moment about. So in this case right here, I'll draw it in orange. This orange is going to be my pencil. All right. So what I'm doing is I'm taking my one hand and I'm holding it at point B. So I'm restraining this end right here. So this is my hand. I'll label it hand. And I'm holding the pencil. And what I'm going to do with my other hand, and more specifically my finger, is I'm just going to put the force. I'm just going to pretend I'm putting a force as it looks in the diagram. And what I'll see is this pencil will start to do this. Slowly rotate like this. And then from there, it's very, very easy to tell that, hey, the general direction's like this. We find out that that direction is actually counterclockwise. So for this case, after we put 4,125 Newton meters, we should also put a little arrow defining in the clockwise direction. So that's how I like to do it. It's probably best to show you guys this in person. I'll show my class, I guess, but if you have questions, just come see me. All right, so that's the first one. Now, the first one's easy because it was already kind of 45 degrees. So, sorry, 45 degrees. I'm making a fool out of myself. 90 degrees. Remember, it has to be that perpendicular distance. So let's move on to F2, which is that 500 newtons right there. So if we look here, we have a problem. The 375 was great because it was already at 90 degrees. But if we look at this angle right here, that's actually not 90 degrees. It's less than 90 degrees. So we can't use that distance of 5 meters. It just won't work. So what we're going to have to do is we're going to have to split this force, and I say forces because we'll have to do it for the next one too, but we're going to have to split this force into x and y components. So we know that this 500 newtons right here has an x and a y component. And that's what's nice about moments and finding x and y components, because x and y components will usually always be perpendicular. So this 500 can be split into two components, which I will do in dark green so they really stick out. So the first one is coming straight down right here, like this. And then the second one runs along B like this. So this right here is F2x. And the one up here is F2y. So this is the only trick that's going to kind of get a lot of students, is those forces F2x and F2y, they act at the point on which that 500 does, that bottom point right here, which I'm going to kind of highlight in purple right there. They act at that point. What a lot of students will do is they'll say, okay, well, F2y is this, and then they'll go, F2x is up here. F2x. And then they'll say that F2x creates a moment at this distance. And then that's one of the most common questions I get asked is, how do I find, and we'll just label that x, how do I find that distance x? Well, it doesn't act up there. It's impossible to find that distance x. So what you have to understand is both of those forces, oops, I'm not going to be able to erase that purple either. That F2x acts at the bottom. So those forces both act at that point on which the 500 touches. And that's very important because from now, when we're finding F2, so F2, what we're going to see is M2 is going to be equal to F2x times the distance perpendicular in the x direction, and then plus F2y times the distance perpendicular in the y direction. And now if we look at this right here, F2x, which I'll highlight real quick, we see that that runs right along B, and it actually intercepts point B. So that perpendicular distance in this case is actually going to be 0 right here. So F2x does not create a moment about B because that perpendicular distance is 0. And F2y, on the other hand, there is a distance. We see that there's a perpendicular distance, and I'll go back to the pink marker, between F2y, and you can kind of see it, between F2y and point B, where there's a length with a perpendicular distance. So what we can do is we can simplify this even more. So M2 is going to be equal to F2y, which we know is just going to be 500. And then we got to convert it to its components. So it's going to be 4 over 5. And then times that perpendicular distance. And in this case, it's going to be 5 meters. So we're going to throw in the 5 at the bottom. And we're going to find is that M2 is equal to 2,000 newtons times meters. And you can tell that this will go in the counterclockwise direction because it's actually the same as the 375. It's still on that side. All right, so now we go to the last one. And again, it acts at an angle, as we see 30 degrees. So what we're going to have to do is split this again into x and y components. So we can tell that this force, and what I got dark blue this time, can be split into this component here, and then a horizontal component like this. And I'm just going to label these, so it's going to be F3x, and it's going to be F3y. So what we're going to look at now is we can write our moment equation. And we can go for F3, I guess we'll write F3. M3 is going to be equal to, of course, F2x times d perpendicular x plus F2y times d perpendicular in the y direction. And in this case, we actually look at F3y actually runs and intercepts point B. So we know that this this d perpendicular in the y is going to be 0. So this doesn't create a moment again. And I guess I'll cross this one out too because this one didn't create a moment. So now we see that M3 is actually just going to be F2x, which we know is going to be 160 newtons. But then again, that's F2 just in general. So to find the x component, we're going to have to multiply by sine of 30. And then we have to multiply that by the perpendicular distance. So if we look in this case right here, I'm going to draw the pink line. If I'm going from point B to that force, perpendicular distance, well, F3x is perpendicular there. So that distance there, 0.5 meters. So from here, I'm just going to put in a 0.5. And what happens is I'm going to get this as 40 Newton meters. And now, well, what's the direction? So again, what I would do is I would take my pencils. So I'm going to draw this out again. It's so much easier just to show you guys in person. So I'm just going to pretend to draw a pencil. What I'm going to do is I'm going to take one of my hands and hold it at the point, which we want. This is point B. And then we also know that the force is going to act something like this. So again, I'm going to have one hand at point B holding that pencil into place. I'm going to take the finger of my other hand and just push on that pencil in the direction of the force. And what you'll see is the pencil will start to rotate like this. So we know that the general direction of this rotation is this way, which again, like the other forces, is counterclockwise. So we're just going to put a little counterclockwise here. And I'm just going to erase all this because we don't need it. And I'm just going to state my final answers because that's one thing that's very important. So I'm just going to go M1 is equal to, and we have 4,125 Newton meters. So Newton times meters, that's going counterclockwise. We know that M2 is equal to 2,000 Newton meters. That's also going clockwise. And finally, we know that M3 is equal to 40 Newton meters, and then that's also going clockwise. So I'm just going to highlight the final answer, and then we're just going to discuss some things that we see real quick and try and relate them to real life. So as you guys can see, there's a very, very big difference between some of these, M1, M2, and M3. And of course, one of the biggest differences, of course, is just the magnitude of the force. As we see from the 500 in F2, we go down to 160 in F3. Now, what this tells us is that, yes, that's a big jump, but if we look at the magnitude of moments, it doesn't really reflect that jump. It dropped down a lot more than the drop in force. So the biggest thing that really happened wasn't so much the change in force, but the change in distance. So the magnitude of a moment is very, very dependent on distance. And that's one of the most critical things. And in structural engineering, it's one of the biggest things. One of the biggest challenges we have is increasing the span between columns. So the beam that runs between columns, making that span as far as possible. And it's not to do with strength, it's to do with moment. Because if we have people acting at that center of the beam and we expand further, it's going to create such a big moment because of the distance between the person on top of the beam and the column. And the best way to kind of think about this, the way that I was explained to kind of help, is just think of a door. When you open a door, you put your hand as far away from the hinge as possible. You open it at the center of the door. If you try and open a door right at the hinge, it's going to be very, very, very difficult because you're not creating a big moment. You're going to have to apply more force to create the same amount of moment. So it's just kind of interesting stuff. Again, 2D, it's kind of here to kind of introduce you to moments, but again, it most likely won't be on the midterm. You guys are going to start dealing with 3D, and in that case, it's kind of the same as particle equilibrium, where things kind of change a lot, but the concepts are the same. if you know what I'm saying, but we'll get to that later. Again, this will be very important after the midterm, though, because in that case, it's all 2D. I'm just trying to think. Yeah, it's all 2D. And you'll have to deal with moments of a bunch of forces. So thank you all for listening, and I'll see you guys in the next tutorial.